Okay, so we will be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, thank you. So we're going to finish up around the steady state error, topic. And let's look at the following situation. Now, up to this point, the only types of systems that we were looking at, or transfer functions that we were looking at, were forward transfer functions of unity feedback systems, meaning that there were systems that the feedback was a unity feedback. Or in other words, we didn't have a transfer function in the in the feedback loop. Now, to do, if you guys remember, the steady state error calculations and formulas that we derived were based on a unity feedback system. So what happens when we have a non-unity feedback system? Well, we can use some algebra. We can use some, yeah, it's called this way. It's like block diagram algebra or manipulations to convert the feedback system into a unity feedback system. And so what do? We've got this system here, which is a system that has both a forward transfer function, which is g of s, but also has a feedback transfer function, which is h of s. Now, we want to somehow turn that into a unity feedback system or an equivalent unity feedback system. So we're going to do the following steps. So what we're going to do is the following. Give me a moment. Okay. And so what we're going to do is the following. This is the original transfer function that I had right here. And I'm just going to do some algebra. Remember that here we've got a summing point. So the only thing that this little circle does is that it adds whatever I'm putting there. So basically what am I doing? I'm going to add a loop here. That's going to be a unity loop. So I'm adding here the unity loop that I want. Remember that a unity loop is equivalent to having a transfer function here, a box that has a 1 in it. But we represent that as a unity. So if I don't want to alter anything, what I'm going to do is that I'm also going to add another box here with a -1, right? So since this here is the summing point, I'm really not changing anything. I'm just adding a 1 and I'm subtracting a 1. So I'm really not modifying the system. Now, I can grab these two. And add them algebraically here because they're going into the summing point. I can add these two and it's equivalent to this box that I've got here. And lastly, this block that I have here, let me use another color. I haven't used green. Let's use a yellow. This block, or these two blocks that I have here, is the typical feedback loop. And remembering that when I have a feedback loop like this one, the transfer function is going to be g of s divided by 1 plus g of s h of s. So basically taking that into account, I grab the yellow blocks that I have there. And this turns into this once we do this operation. Okay. So basically what we've done here in this sort of explanation is that we've converted this, which is the feedback system that had a feedback loop transfer function. We have converted it into this, which is the equivalent system. It's the equivalent system. It's the same system, but it's represented as a unity feedback. And so I can go from the purple to the green, and now I've got a forward transfer function, a new forward transfer function, which is this one. That is the one I can use for the steady state analysis with the expressions that we've derived previously. Okay, now it's not that I'm bored about my whole class. It's that part of this thing I have is that I've got a lot of allergies. I'm really, really congested, and so it makes it hard to breathe. And after the COVID, it's been up and down with the breathing, which is not fun. And so I try to make myself yawn, because when I yawn, I can get a full, like now, I can at least get a full breath of air into my lungs. So, but yeah, I get it that my class can be boring. My class is so boring that the professor can fall asleep. That's recorded. Somebody wanted to say something. I'm sorry.
Yeah, if you're not feeling well, you could as well like put us to watch some videos and we can continue later.
You're a good man. You're a good man, Miguel. I appreciate it. I really appreciate the suggestion. I know you guys don't want to have class, but no, I want us to finish this up. I'm better than Monday, but I can move on. It's a long day today. It's a terribly long day today. I've still got class until 10 p.m. But the only thing that's going to happen is that you're going to see me yawn. But thank you very much, Miguel, for the offer. We'll do the videos on another occasion.
You're welcome. Whenever you're feeling down, just let me know and I'll be there.
Thank you so much, Miguel. Thank you so much. I'll keep that in mind. Thank you. Okay, so now let's look at an example where we've got a system that's got both the forward and the feedback transfer function. So we've got the forward and the feedback transfer function, and we want to analyze the steady state error for the system, but we want to know what the behavior is. However, we've got both of those transfer functions there. So what we need to do is that we need to convert this, first of all, into a unity feedback system. So we're going to use the expressions that we just saw. Okay, so, oh, whoops, I've got these slides hidden. So let me unhide them here. There we go. So what are we going to do? We're going to use the expressions that we had. So we want to turn this, which is on the left-hand side, we want to turn it into this, which is the forward, I'm sorry, the unity feedback. So we've got G of S in this case. This one that we've got here, this is G of S. And over here, we've got H of S from the bottom. We've got H of S here on the bottom. And so we want to grab these two, put them in here so we can find the new forward transfer function, which is this one that we've got here. So we're going to have, I'm going to write it down here on the bottom. We want to get this one here, which is the one we need. And it's going to be G of S, which is 100. I'm going to write it down with colors. That'll make it more fun. So it's going to be G of S, which is 100. Try to follow along and do this on your notes. S plus 10. And in the denominator, we are going to have 1 plus g of s times h of s, which is going to be 100 divided by s times s plus 10. That is going to multiply h of s. And in this case, h of s is going to be 1 divided by s plus 5. Minus g of s. Hmm, 100 divided by s times s plus 10. Okay, that's going to generate the new forward transfer function that we're going to need for the system. So this is going to be equal to, let's do some quick simplification here. I'm going to multiply everything times s times s plus 10, and then we're going to do some simplification there to see if we can get something a little bit more manageable. Okay. I'm going to multiply everything by s times s plus 10. I'm going to multiply everything times the common denominators, which is s times s plus 10 times s plus 5. That would be the common denominator. So what I'm going to get is, I'm going to write this in green. I'm going to get, I'm going to write it in, let's say let's use pink. It's going to be 100 times s plus 5. Try to do this yourself so you can practice some of your algebra times s plus 5. And check me if I get any mistakes, by the way. And here in the denominator, we're going to have s times s plus 10 times s plus 5 plus, over here, we're just going to have the 100 and over here, we're going to have minus 100 times s plus 5. I think that's correct. Okay. And the result we're going to have, and I'm going to write that down in green, which is what we're looking for, the forward transfer function, is going to be, the numerator we can leave as it is. We can just leave it as 100 times s plus 5. That's fine. The denominator, let's see what we've got in the denominator and help me out with the calculations. We're going to have, let's see if I help me out here with the calculations. Let's see if I don't miss something. I'm going to try to do them in my brain. It's going to be S times S is going to be S squared times S is going to be S to the 3. We're only going to have one S to the 3. Okay. Then it's going to be 10S plus 5S is going to be 15S, right? 15S times S is going to be plus 15S squared. Okay. Eliminate these parentheses. I don't want where they look. Check me to see if I don't have a mistake. Okay. Then it's going to be 10 times 5 is going to be 50 times S is going to be 50S. Okay. However, we've got a minus 100S over here. So 50S minus 100S is going to be minus 50S. And lastly, that's this one. We have 100 here and we have minus 100 multiplied by 5. That's going to be minus 500 plus 100 is going to be plus.
Minus.
I'm sorry, minus. Correct. Good job. Good job. Thank you. Minus, what was it? 50, right?
400.
400. Okay. And this green transfer function is going to be what's up here. That is going to be the transfer function that we can use to do the steady state error to find the steady state error. Okay. Let me save this here. Okay, before we move along, give me a moment. Okay, so now we've got the transfer function of the forward transfer function for the new system that's equivalent, that's now a unity feedback system. So I'm going to erase this one here. Questions with this one before we move on? No, I hope I didn't. I think the calculations are correct. I hope I didn't mess something up. So so now we've got the transfer function, the new transfer function here. And let's just remember that this is equivalent to having then now this. This is the new system. It's going to be a unity system, feedback system, which is equivalent to the original one. Okay, this is the output CLS and the input ROS. Okay. Now, the first thing that we're going to try to, or the first thing we need to identify is what, can somebody tell me what type of system this is? Can somebody tell me the type? Anybody?
Type 2?
No. Remember, type 0, Angelica, correct. The type, remember, has to do with the lonely S that we're going to have here in the denominator, multiplying whatever is in the denominator. And so right now we don't have any S, so that means that we have an S to the 0. So that means that it's a type 0 system. Okay, it's a type 0 system. Oops. It's a type 0 system. Now, we can do all of the calculations if we want, but remember that we really don't have to. What did we say? What did we say about the type 0 systems? What are the characteristics with regards to all of these calculations? Can somebody tell me or remember that? Pablo, go ahead, please.
If it's a type 0, it's gonna be a ramp that has an error, and the other ones are gonna be 0 and tending to infinite, like the
Mhm.
error.
Okay, let's verify that. Let's just go back over here. Thank you, Pablo. Let's just okay. I'm gonna leave the drawing there. Let's go back over here to our table. I don't want to remove that drawing, so sorry about that. So if it's a type 0 system, actually, if it's a type 0 system, the constant error is going
It's
to
a
be
step.
in the step,
Yeah,
and the
yeah.
rest are going to be infinite. So this is a type 0 system. So the only type of input that's going to be valid or error that's going to be valid is the step. And remember that we did a couple of exercises. So for the type 0 system, we had for the type 0 system, we had the limit when s tends to 0, which was kp of g of s, gave us a constant value, and so the error was constant, but the rest gave us infinite. So the same thing happens here for this case. So if since it's a type 0 system, we only need to calculate this one here. So the only error that's going to happen or going to occur, which is going to be a constant error, is for the step. The rest of them, this is going to be, these two are going to be 0. As well, and in the case of these two, I'm sorry, since the constants are 0, the errors are going to be infinite. So we only need to calculate one, which is the step. This system can only could only follow position. So we're going to do that. We're going to say that Kp, help me out with the calculations here, everybody. Kp is going to be equal to the limit when s tends to be 0 of g of s. So I'm just going to go back over here to this one. And if I look at the transfer function, if I make S 0 here, this one's going to be eliminated, this one, and this one. And I'm just going to be left with 5 times 100, which is 500 divided yes, 5 times 100, which is 500 divided by minus 400. Okay. Okay. So this is going to be 500 divided by minus 400. Can somebody give me that value? Please do that quick calculation.
Minus 1.25.
1.20 minus 1.25. And the error in this case, step error. Let's write this. When it tends to infinite is going to be equal to 1 divided by 1 plus Kp, which in this case is going to be 1 divided by 1 minus 1.25. Okay. What would that be? Can somebody tell me?
Minus 4.
minus 4, okay? And so this would be the error for the step that we've just calculated. Let me give a quick save here, okay? Okay, and so when we have a transfer function that, or a system rather, that has that doesn't have unity feedback, we can still calculate we can still calculate or still evaluate the steady state error by converting it to the equivalent system using the expression that we just saw. Okay. 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 Now we are going to jump over to the next topic, which is an interesting one that has to do with, oops, there we go. I saved it. I hope I saved it. Yeah. Okay, which has to do with the concept of the root locus. Okay. Now, up to this point, we've seen that that the root what we've seen up to this point is that if I have a transfer function, the behavior of the system, as well as the stability characteristics of the system, and the steady state characteristics of the system, in the end, they are all going to depend on the values and location of the roots of the transfer function in the S-plane. So depending on where the roots are in the S-plane is how the system's going to behave, basically. We've seen that if any of the roots are on the left-hand side, right-hand side, I'm sorry, that meaning that they have a positive real value, then the system is going to be unstable. We know that if any part of the root or any pair of roots are or have an imaginary component, that has to do with the damping ratio and the overshoot. If all of the roots are along the real axis, then we know that that has to do with that has to do with systems that are over damped, that don't have an overshoot, for example. And so again, the location of the poles of the system is going to give us or tell us information as to how the system behaves. Now, if I have a system where I can modify any of the parameters like we've seen, where I've got a certain gain, for example, K, that if I vary or change the value of K, I'm going to change the behavior of the system. We already saw that when we did the lab exercise of the antenna. We saw that when we varied K, the antenna behaved differently. Well, what would happen, or wouldn't it be useful to be able to look or know all of the possible values of possible roots for the transfer function, poles of the transfer function, for all of the possible values of K? Remember in the lab exercise, I asked you to give values of K until you found that the system was unstable. And you just randomly gave values to it. But wouldn't it be useful to be able to map out all of the values of the poles for all of the values of K, and for that to help us analyze the system, but also do design based on the system? So that is what the root locus is. The root locus is going to be a graphical representation of all of the possible poles that a system can have for all of the possible values of K, considering K a parameter that we can modify or change. Now, does anybody know what the word locus means? So if you don't know what the root locus means, the word locus means, well, root locus, you can remember that. Locus means location. It means a location. A locus is a location where you find something. So this is why it's called the root locus, or the location of the roots. Okay. So let's analyze this and let's see how this tool can be useful for system design, and also how it can be used how we can use MATLAB to find it. So let's look at the following system. We've got this system is trying to represent the positioning, a positioning system for in this case I believe it's a camera. And so it's got a transfer function here. It's got two transfer functions that are in series. We've got K1 and K2. K1 is the amplifier. K2 is a parameter for the motoring camera. And we want to trace the root locus, or rather, we want to see all the possible values of the poles of the system, according to all the possible values of the parameter K that we can that we want to modify or analyze. Now, these couple of transfer functions that we have here, these can be actually compressed into having K1 multiplied by K2. So this is equivalent to this. K1 multiplied by K2 divided by S plus S plus 10. That's equivalent. Now, since that's equivalent, and to try to simplify, and to try to simplify things a bit, then instead of having two parameters, this is equivalent to having, well, just one parameter that I'm going to call K. That is going to be equal to or equivalent to the multiplication of those two other parameters. And that's actually the way we're going to approach the design. We can have many parameters, but we can actually join them up into one. And then once we have the value of that parameter, which is a composite parameter, then we can set the value of one of the parameters and find the other one. So K is going to be equal to K1 and K2. So this transfer function is also going to have a characteristic equation. And that characteristic equation is going to incorporate the poles of the system. And the poles are going to depend in the end of the value of K. Okay. So let's see how we could trace the root locus manually at first. So if we were to do this manually, well, basically we would give values to K. And for each of the values of K, we would evaluate the characteristic equation. And I'm just going to write that characteristic equation down here just so we have it and can reference it. So the forward transfer function is going to be K divided by S plus 10. I think it was S plus 10. And so the whole transfer function for this system, which is going to be C of S divided by R of S, is going to be equal to, remember, it's G of S, which is K divided by S plus S plus 10, divided by 1 plus G of S. It's a unity feedback, divided by K S plus 10. And so if we simplify this, what we're going to get is k divided by s squared plus 10s plus k. And we have to remember that in the end, the roots for this system, I'm sorry, the poles for this system are going to define the behavior of the system. And so those roots are going to be given by this equation here on the bottom in the end. And so if we start evaluating that expression, we're going to start evaluating it. We're going to give values to k. We're going to give different values to k. For each value of k, we obtain the poles. And then what we do is that we take these and we plot them. And we find this graph here. So we're just plotting the values here. And once we plot them, we can just make a continuous line between them. And so basically the root locus for this system is going to look something like this. So the lines I'm drawing in blue are the root locus. That graphic, which in this case is a kind of like it's a cross, that graph represents all of the possible values of the poles for all of the possible values of k. For a second order system like this one, it's always going to be a cross. Depending on the order of the system, it starts getting much, the root locus starts getting much more complicated looking. But doing it manually like we did it here can be a little bit complicated and even long and tiresome when we have more complex systems. So we can use some tools to be able to create this graph in a more efficient manner. The root locus has properties. First off, the multiplication of k, the values of k, times the forward and feedback transfer functions, the absolute values of those is always going to be 1. And the angle to each of the roots multiplied by k is always going to be a multiple of 180 degrees. And these are called the magnitude and the criteria angle. So in the previous example, all of the values that are found here in this graph comply with these two rules. So if we grabbed any value here, any value, and we substituted that value into the expressions for g of s, h of s, and multiplied it by k, we would get, in the case of the magnitude rule, we would get a 1. And in the case of the angle rule, we would get a multiple of 180. All of the points in the root locus comply with these characteristics. Okay. Now we're going to see how to do the tracing of our root locus or the plotting of the root locus, but we're going to, instead of doing it manually, let's make use of MATLAB to be able to do that and be able to have a software where we can have the root locus represented there, and we can actually use the root locus to do some design. Okay. First off, a couple of things that are important. When we, similar to the steady state error, when we're working with the root locus and working particularly in MATLAB with the root locus, we have to identify the forward transfer function. So again, we're assuming that it's a unity feedback system. So this is g of s, and this is the transfer function that we're going to be using for the functions in MATLAB and to be able to calculate the root locus. If for some reason, and this is unity feedback, if for some reason the system does not have unity feedback, then we would have to do this procedure over here that we talked about. We would need to do this procedure to convert it into a unity feedback system. Okay, we need the forward transfer function to be the only thing we have. Okay, so in the feedback we should only have a line or a one. Okay, so let's see how we can do that in MATLAB. There we go. Okay, so what we're doing now is that we are going to be using this, we're going to be using MATLAB to trace the root locus, okay? And again, we're using MATLAB so we don't have to do it manually, and we use a root locus for analysis and design, which is really the strength of using the root locus. So what I'm doing now, I'm switching over here to MATLAB, and I'm going to be defining the transfer function, in this case g of s, which is the forward transfer function, this one that we have here without the k. Okay, and so I'm going to be defining that one over here. So I'm going to say sys. First, we do a clear all, then a CLC. You can follow along if you wish. I'm going to define the forward transfer function. Sys_g is going to be the transfer function of, in the numerator, we've got as s plus 3, so it's going to be a 1 and a 3. Then on the denominator, we've got 4 factors. There are s times s plus 1 times s plus 2 times s plus 4. So it's going to be a series of convolutions there. So it's going to be the convolution of s, which would be 1, 0, times the convolution of the next term is s plus 1, which would be 1 and 1, times the convolution of s plus 2 and s plus 4, which would be 1 and 2, bracket there, 1 and 2, and 1 and 4. And then just let's close up the parentheses and verify that we're not missing any parentheses there. Let's hope we aren't. And so this would define sys_g, which is the forward transfer function. And once we have the forward transfer function, then we can do the root locus or trace the root locus using MATLAB. Okay, so there's a function called root locus. It's not called root locus in MATLAB. It's called R_locus. So if we click R_locus here, help R_locus, we can have the description of the root locus function and what the function receives. And so what root locus receives is that it basically uses the forward transfer function, which is the one we just defined. And with that transfer function, it plots the roots. It can also be defined to just trace. So the root locus is basically going to trace the roots from when k varies from 0 to infinite or to a very large number. But we can also give it a set range of k if we want. So there's this version of R_locus where we can give it a vector of k, where I say I only want you to evaluate for this range of k. We can also do that. But right now, let's trace the whole root locus for this system. So I'm going to say R_locus of sys_g. It's going to take a little bit here. I'm not saying this is a complicated process, but it's a bit complicated for MATLAB, might be. So this is the root locus for that system. By the way, depending on the order of the system, if it's a second order system, it's usually going to be a cross. If it's a third order system, it's going to look kind of like this. It's going to be kind of like this U with some lines on it. Fourth order, they start getting, fifth order, they start getting really, really weird. Let's analyze this and look at a couple of things. You notice that there are different colors. So the different colors are different sections of the root locus. The root locus is usually drawn in sections. and the sections have to do with a particular variation of K. And the little circles and crosses that we have here are going to be the, are going to be the poles and the zeros of the system for a particular value of K. In this case, when K equals, I believe when K equals 0. And we notice that here we have the reference of the 0 of the S-plane. So we know that any part of the root locus that's on the right-hand side is going to be a part of the root locus that where the system is going to be unstable. Now, why is this graph useful? Well, because in this graph, I can click any part of the graph, for example, here. And for that particular point of the root locus, what information do I get there? Gain is the value of K. So for this particular value of K, the pole is minus 7.08. I have a damping of 1, an overshoot of 0, and the natural frequency is 7.08, a rough equivalent to a second order system is what it's doing there. For example, if I click on another point, let's click on a point here. The value of K here is 5.13. And the damping is going to be 0.129, and the overshoot is 66.5. This is extremely useful because I can kind of just look through the points and find points within the root locus that give me values according to the parameters or design parameters I'm looking for. Now, for example, if I select a point over here, this is a gain of 76.3. The pole has a positive element. Notice that it has a negative damping ratio. That's another characteristic. If we have a negative damping ratio, the negative damping ratio gives me an indication that the system is also that the system is unstable. The overshoot is going to be 231%. Obviously, it's a system that doesn't have characteristics of stability. So, and again, the value of K is this value of gain that we have here. So the root locus can be really useful to find, to be able to locate these parameters and use it as a design tool, an analysis and a design tool. Now, one thing that I can do here, I'm going to delete these. Is that we can also kind of use this graph to kind of go along the root locus, kind of trace it. So I can set a point here and I can kind of trace it to just kind of find the value I want. So let's assume that, let's use this as a design tool. Let's assume that for this particular system, which is this system that we have here, for this particular system, I would like the system to have, or I would like the system to behave in such a way where the overshoot would be less than 10%, for example. Less than 10%. So I know that if there's going to be an overshoot, then I have to have an imaginary part. So it has to be in one of these sections. So what I'm going to do is that I'm going to do a zoom here. I selected the zoom tool. I'm going to do the zoom there just to kind of zoom in on that section. I'm going to deselect the zoom, and then I'm just going to trace it here. So here the overshoot is very low. I want to go to the, what did I say? Did I say 10%? Let's assume that it's 10%. So if I go through here, I notice that around the gain of 1.18, I start to get an overshoot of 9.74. Okay. I can go further along here depending on your pulse. And if I go to actually a higher gain, there's a point where the overshoot gets to be more than 10%. So I know that it's around this region. I'm going to do a larger zoom on that region. a more finer trace here. Oh, it went over. So I'm just tracing it here. So the mark of 10% is going to be around a gain of 1.2. So any gain that is lower than 1.2 should give me a lower overshoot. Now, by the way, can somebody tell me what would happen if I would look in the lower part? So right now I'm looking at the upper part here, which is a strong blue. But what if I did the same thing here on the lower part? What would I find? Can somebody tell me? Can somebody kind of catch what's happening there? Try to do a zoom out. So right now I'm looking, I just decided to look over here on top. And I got that value. Why didn't I look on the bottom, or what would happen if I do exactly the same thing on the bottom?
Well, the negative side is going to be the imaginary is going to be negative, but I don't really know what would happen.
Yeah, so that's my pulse isn't too good. That's why I'm not hitting exactly the same mark when I'm going over. So what's happening here is, remember that poles come in pairs. That poles that have imaginary parts come in pairs. So if there's a pole here on top that's minus 0.375 that has a gain of 1.19, there's going to be a corresponding pole that should be roughly around this position here that's going to have the same real value, minus 0.375, but it's going to have the negative imaginary part. So the poles are always going to come in pairs. So let's see what happens when I start looking here on the bottom. I just start tracing here on the bottom. If I go here to this spot, my line wasn't exactly. I want to see
It is just like a mirror.
Yep, correct. That's exactly it's a perfect way of describing it. I think it was Jose that popped up. Perfect way of describing it. It's a mirror. It always has. That's one of the characteristics of the root locus. It always has to be symmetrical with regards to the real axis, because the imaginary the poles that have imaginary parts are going to have a mirror effect. That's exactly a great way of describing it. And notice that we're not doing exactly the same. We're not doing exactly the same value here. So I got a 1.19. And so remember that we're always going to have two pairs of values here. The gain is going to be the same, but the effects could be different depending on how we analyze the system. So I think it was 1.2. So let's go back over here and let's go back over here to MATLAB and let's let's see what happens with that. Let's see what happens with that gain. So I'm going to say that K equals, I'm going to say 1.19. Okay. Just have a close value to 1.19. And then I'm going to say that cis, what example is this? This is 8.2. Cis 8.2 is equal to the feedback of K times cis G, comma 1. So I'm just generating the whole system. Okay. And let's see what happens with the let's see what happens with the step function. Okay. And so the original cis G was this one, and so the The complete feedback system is going to be this one, and let's run a step function. So let's see what happens. It's going to overwrite the other. It's going to overwrite the other graph. So the overshoot it's 9.53. It's less than 10%, which was what I wanted in the end, with a setting time of it's a long setting time. It's about 9.76 seconds. But at least with regards to some of the parameters that are going to have to do with the damping and the overshoot, the root locus can give me an idea of how to find values for the system that can be used for design. Now, let me clear this one. Close this window up. Now let's do the root locus again. Remember that we're doing it for sys G. The other thing is that we can kind of identify the boundaries for stability. That's another thing, the boundaries of K for stability. So again, if I do a zoom of this part here, I know that anything on this side is unstable, okay? Anything on this side is the system is going to be unstable, okay? So I can actually go through the values of K and just kind of go through them and see that the value of K starts getting larger until I get around this point here. And we can actually do a zoom there, which is the point where it reaches the imaginary axis. And I'm just going to find here approximately the value, where we start getting right now the pole is still negative for 9.64, but if I go to 9.66 approximately, I already have a pole at 0.0038. This is positive, so the system is going to be unstable. So the range for stability is going to be approximately around 9.6, between 9.64 and 9.65. So let's see what happens in the system if I say that K is equal to, I'm going to say 9.65. Let's see what happens there. So we're going to do the feedback again, and let's do the step again. So lo and behold, we're going to have an unstable system for that value of K. It's going to start getting, it's going to be flat, and then boom, it's going to start going unstable. So we can roughly find the values of stability also, or the range of stability going through or using the root locus plot, which is also going to be useful. Okay, so this is just a summary of, you're going to have this in the PowerPoint. This is just a summary of the root locus, the root locus plot and the code that was used for that. Now let's look at this system over here, just so we can see another example. So I'm going to clear the command window here. Clear command window. Okay. So now we've got the transfer function that we're going to be using. I'm just going to copy paste this. The transfer function is going to be, we don't have anything in the numerator, 1. And in the denominator, we have an s plus 2, s plus 4, and s plus 6. So we're going to have, we're going to have the convolution of 1 and 2 multiplied by 1 and 4 and 1 and 6. Let's just verify that our parentheses are correct. So it's 1, 2, 3. That's going to be cis G. Let's plot the root locus. For this system. What will I do there? We're going to get a very similar one to the one we had before. This system is it's a third order system. The previous one, I'm sorry, was a fourth order system. It's going to have a very similar characteristic as the other one. Okay. And again, we can also find values here that can be useful. So for example, for this system, if we go along here, we're going to find this system can have a higher gain. We're going to have around here 470, around 475. Yeah, between 460, 75, approximately 480. It's approximate the range for us to get into an unstable region. Okay, so this is another example as to how we can plot the root locus. Okay, and this one that we have here, this again is the example that I just showed you and the MATLAB code. Okay, now let's look at this system. It's a simple system. For the following system, we want a maximum overshoot of 20%. We don't want an overshoot that's less than 20%. Now, some of you may be saying, well, then let's go for an overshoot of 0. But remember that if we go for an overshoot of 0, we can do that, but that's going to make the system slow. So if somehow we're talking about a maximum overshoot, it means that the overshoot is allowed to make the system quicker, but we don't want it to go larger than 20%. And also to kind of find an approximation to the ranges of K for stability, instability, and marginal stability. So let's do that. For this example, I'm going to clear the command window. So this is a very simple system. So clear all. Cis G is going to be equal to the transfer function of 1, comma, the convolution of 1, 0, comma, and 130. Okay. So that's the transfer function. Let's look at the root locus. This root locus is just going to be the cross because it's going to be a second order system. It's a very simple root locus. I think I already opened it up in another window. Here we go. It's going to be a very simple root locus. It's just going to be a cross. So if it's got an overshoot, we know we have to look in the part that has an imaginary component. So let's just click on any of these here. So for example, if I click there, the overshoot is 0.246. It's still a very low overshoot. If I keep on going over here, up to this point, we've got an overshoot of 7.5. What I can do also is I can use a little hand icon and drag this. And I can keep looking. Oh, now I've gone to 21.6. So the limit here for the 20% overshoot is 1.08 to the 3. That's 1080 approximately. So let's give it a value of 1080 and see what happens. 1080. And I'm going to do the feedback. Before I do the step, I'm going to do the following because I don't want to remove the root. Remember that in MATLAB, if you call up a function that does a plot or a graph, and then you call up another function that does another one, it's gonna put one on top of the other. So I'm just gonna call the figure to open a new one, and then I'm gonna do the step of, this isn't sys 8182. This is this example. Oh, this doesn't have a number. So instead of calling it sys82, I'm going to call it sys r root locus x sister x. Call it. And I'm going to say again that k equals 180. Well, I didn't remove it anyway. And let's do a figure and a step of sys x. See what happens there. And so we're just in the brink of the 1.2 of the. So we've got exactly an overshoot of 20% for that gain. Okay, I'd say we give it so we know that for 180 the peak amplitude is 1.2, so there's a 20% overshoot. So let's give it a value of k of, I don't know, 1,000. Let's do the feedback again. Let's do the step again. And now we notice that the overshoot got lower. So now the overshoot is 18.4, so it's gone lower. And if you notice, with the root locus and using MATLAB as a tool, we can really play around with these values, and it can help us define these ranges for our system for different values and different performances. Okay, so now at least I know that if the value of k for a 20% overshoot is 1,080, well, now I can play around with that, and I know that at least if I give it lower values than 180, the overshoot is going to go down. Okay, so that can be an interesting design parameter or tool. Rather. A moment here. Okay. Now let's go back and look at the root locus, and let me just run it again. And so what are the ranges for stability for this system? Well, if we look at the root locus, the interesting thing about this root locus here is that the root locus, if we do a zoom here in the place that's close to the x-plane, we notice that the root locus ends here at, I believe this is going to be 0. It ends here at 0. So there are actually no values of k that are going to make the system unstable. So there's no values that are going to give it or generate negative roots. And we actually don't have any values along the y-axis. Okay. So that's also not going to give us any sort of marginal stability factors for this one. The other ones that we saw did have those characteristics. Okay. Okay. Good. Okay. Questions up to this point? This kind of rounds up Unit 3. We're going to do a lab exercise on Monday where we're going to be working with these with some examples and doing some design. But questions up to this point? Nope. Okay. Good.